Professor Yadav from the Indian Institute of Technology, Roorkee. Please.
Thank you, Chairman. Thank you all present here. So myself, Vinay Kumar Yadav from Indian Institute of Technology, Roorkee, going to present a part of my work, that is I'm doing my PhD work. So this is the effect of corrosion on fatigue behavior of welded aluminum alloy 2024 in T3 metallurgical state. So the outline of my presentation will cover the motivation why I'm doing this kind of analysis, and the behind the motivation, what was the experimental methodology that I have been used, and then we'll discuss about the results, and based on results I will conclude myself. So motivation of doing this work is that as we all know, the life of a component obviously depends upon numerous factors, but we are dealing with some factors, so we just mentioned it a little bit, that the material's microstructure, how it behave in different manner, and the applied load, that we are applying the constant amplitude loading or variable amplitude loading. It also affects the fatigue life of a component, especially the use in the aerospace component, and also the environmental conditions we are using, and the kind of residual stresses, because this is inherently produced in the material, whatever the process we are using to produce the material. So in this, and as we all know that there are aerospace structure, in order to produce a large plate, a large structure, the weld joining technology has been used. But in conventionally, there are people uses a lot of rivets are bolted to join the structures, but add of rivets and bolted join in such kind of a course structure, it is extra weight that reduces the frequency as well as the life. After that, the conventional joint techniques like welding techniques has been evolved and that frequently used in those structures. But these structures has also been, So in these welding joint, we can say that there's a lots of porosity and hard cracking arises during the welding, and the kind of dendritic formation occur in the aluminum 2024, and very high residual stress also be over there across the welding joints. These cumulative effects of porosity and dendritic masses, so along with the residual stresses, affects the serviceability of the component under real life application. So to overcome these disadvantages, a new welding technology has been developed, a solid wasted welding technology that has been developed by the Welding Institute in 1991. So this welding technology has a very advantageous over the other conventional technique that has been used. That it uses a non-consumable tool that reduces the weight of the structure up to 15% as well as the cost. Because of the non-consumable tool, there is a lesser residual stresses rises in the joining material, and the non-consumable tool that I'm talking about, this is like something like this. The geometry is up to the people, depend what they are using, but in my analysis, what I'm using, there's a cylindrical tool. The tool is categorized into 3 parts. One part is the pin and solder, and second one is tank. So this technology uses a milling machine, customized milling machine in order to produce the weld. That utilizes the frictional heat between the tool as well as the material plate that is going to be welded, and with the heat of that heat, the material plasticize and join. So this technology has similar fashion in microstructure behavior like conventional technique, because in conventional welding joint we see then there is a heat affected zone base material like this. This is also a combination of these things, because we are so already discussed that there is a stirring process in the material with the help of tool, so we get the sterilization in the nugget zone. This is called the stir zone or nugget zone. Due to the stirring action, the grains within these regions are recrystallized and uniform and more stable as observed through the EVSG data. And also, if you move besides from left or right, we will get the thermomechanical affected zone. In thermomechanical affected zone, the flow material starts from inward to outward. That's why there is the grains are elongated and twisted. And after the thermomechanical affected zone, we will get the heat affected zone. As we all know that heat affected zone is some kind of grains is similar to the base material, but some kind of coarsening over there. So these kind of geometrical heterogeneity in terms of microstructure across the weld significantly affects the mechanical property as well as the fatigue life, either we talk about in air or we talk about in corrosion environments. So my motive is to perform the corrosion analysis at each and every portion of the joint so that I can investigate how it behaves in some kind of a corrosion environment. So I have just taken the two zone, basically the heat affected zone as the welded nugget zone, and compared the data. We have performed some kind of electrochemical analysis using the EIS from the Gamry, and we have compared the data with the base material. We have seen that the welded nugget zone has a better corrosion potential in terms of capacity loss as compared to the heat affected zone and the base material, because the welded nugget zone is I have seen the previous present slide that the very refined microstructure, so that will offer the more barrier against crystallographic pitting corrosion as compared to the heat affected zone and base material. We also try to improve this resistance with the help of some kind of heat treatment. As we all know that with the heat treatment, the properties of getting enhanced property. So we just try to add the heat treatment condition of 493 degrees for 2 hours in solution treatment, and then provide artificial aging of 200 degrees Celsius for 10 hours. And we get there is a deterioration in also the charge transfer resistance. And this can also be seen in the Tuffle curve that the welded nugget zone has a better corrosion potential as compared to the base metal as well as the heat affected zone. Then we try to put the specimen in a corrosive environment for different time interval, the 10 hours, 24 hours, 48 hours, 100 hours, and 200 hours. And we get that as we increase the immersion time, we will see that there is a decrease in the capacity loop as we talk about the welded nugget zone, or we talk about the heat affected zone. And we see that after when we switch from 100 hours to 200 hours, we will get that there is no significant difference in the capacity loss, means the charge transfer resistance. So we stop here myself and to try to investigate its mechanical as well as the fatigue property. We see that if there is no significant difference in charge transfer resistance, so what its effect on the mechanical as well as the fatigue property. So after putting the specimen for different time interval in 3.5 solution, we get that there is a lots of pitting formation over that. As we increase the time, the pitting formation will be more and more. And after when we check from 100 to 200 hours, there is a localized pitting over there. So this localized pitting is responsible for the decrease in the fatigue life, as we see in the upcoming slides. So first of all, we find out the mechanical property in terms of micro hardness distribution as well as the tensile property. And because the micro hardness is also depend upon some kind of the grain structure, so we see that there is a change in the microstructure across the weld cross section. So we find that there is a change in the micro hardness distribution, as well as when we see that tensile property, then when we compare the base material and as well and after the pre-corroded. Pre-corroded, if you talk about the after the corrosion 100 hours in 3.5% solution, we will get that there is a decrease in the ductility of the material as compared to the base metal. Then we go for the fatigue life. In fatigue life, we have applied a sinusoidal load at a loading frequency of 10 Hertz, and using this machine, I have used my MTS 25 capacity machine in order to perform these two tests. So I have considered the two stress ratio. Stress ratio means minimum stress over the maximum stress for the R is equal to 0.1, R is equal to 0.5, and compare the data with the without corrosion and with corrosion. Without corrosion means as well after the weld we perform the test, and with the corrosion means we put the specimen for in corrosion environment for 100 hours, then we perform the fatigue test. And we see that for these two kind of tests, we have taken a standard specimen to ensure that the weld is laid within the gauge section. So if you see that at a higher stress amplitude, there is no significance in the fatigue life of the welded joint component. But as we decrease the stress amplitude, we find that there is a decrease in fatigue life as compared to the without corroded material. This is because of that we put the specimen for 100 hours in the corrosion environment. There is some kind of pitting over there, and crack always initiate from some kind of, if material is in defective or non defective, then always initiate from the pits. So and also examine the SEM that there is some kind of oxides over there. So my conclusion based on these that the crack initiate from these pits are the more susceptible to for the crack initiation. So deterioration in the life of a component with compared to the without corrosion due to the formation on the pits. Then after the high cycle fatigue investigation, I also calculate the crack threshold and crack progression rate in the welded joint. And for the fatigue, in order to calculate the fatigue threshold, I have performed the two tests as recommended by the STM E647, delta K decreasing and delta K increasing test for the two material conditions and the two stress ratio. And we have decreased the delta K till the crack growth rate reaches up to order of 10 to the power minus 10 to the power minus 10 meter per cycle, and the corresponding delta K I have termed as the delta K threshold. And we'll find that with those stress ratio, the only difference is found in the change in the fatigue threshold, and there is no change in no significant change observed in the crack propagation rate in the second and third region of the material. After these, we have also tried some kind of in situ type of corrosion test in my analysis, in which we are just putting the specimen in some kind of a solution chamber over there, and within solution I have put my specimen and apply a sinusoidal loading over there. And regularly we continue measure its pH value as well as the temperature. The pH value kept constant in between 7.9 to 8.3 in my analysis, and we are doing the analysis at 24 hours, 24 degrees Celsius. And the solution we have regularly changing up to 2 days the solution continuously from this defined chamber, and we are not going to stop the test during the test. So after this test is only I'm currently doing, so I do not have much data to show you, but I have little bit data that I am presenting in front of you. So I have performed the two tests at both stress ratio and compared the result that the in situ type of test have a more degradation in fatigue life as compared to the without corrosion or with corrosion at 2 stress ratio. And this is my ongoing work, so there is no data is more available on this. So lastly, I will conclude myself that EIS result basically confirms that the base material as well as the heat affected zone be the most susceptible to the anodic dissolution as than the welded nugget zone. And after heat treatment, the intermetallic particles reappeared over the nugget zone, resulting in the decrease in the corrosion potential and charge transfer resistance of the material, and immense increase in the immersion time from 100 hours to, and after 100 hours to 200 hours, there is no significant change in the charge transfer resistance, indicative that the passive oxide layer formed over the surface protected from the further oxidation, and there is no change in the ferrous region of the crack propagation rate of the corroded specimen. The only change that has been observed in the fatigue threshold, and the corrosion pits that appear in the weld surface associated with the aluminum matrix have the preferential site for the crack nucleation, and thus are responsible for decreasing the welded components fatigue life. And finally, I will acknowledge my institute for providing the infrastructure facility, and also the Dean of Social and Alumni Affairs who support financially in order to attend this conference. And thank you for your kind attention.
Thank you for the nice presentation.